Okay, last week, yeah, in chapter 2, we studied this heat equation, and we derived this heat equation in Cartesian coordinate system. So this is the equation that we are going to use to solve heat conduction problems in chapter 3 and chapter 5. However, Cartesian coordinates is not the only coordinate system that we are going to use. So this is the heat equation in Cartesian coordinate system. And we have heat equation in cylindrical coordinate system. And spherical coordinate systems. Okay? So let's go with the easiest one, the Cartesian coordinate system. So how can we solve this problem? How can we solve this partial differential equation? Second order partial differential equation in x, y, z, and we have time dependent term on the right hand side. So how can we solve this one? We are going to make some assumptions such as constant thermal conductivity, constant K, then this K comes out. And when K comes out, we can divide by thermal conductivity K. Then we can cross this K on the left-hand side, and we have K in this heat generation term, and we have density times specific heat over thermal conductivity K on the right-hand side, which is the inverse of thermal diffusivity alpha. By the way, thermal diffusivity, by the definition, thermal conductivity K divided by density times specific heat. Okay? So if you have rho Cp over K, that is going to be 1 over alpha. Then we can say this is time independent. In other words, steady state. If we say it is steady state, you can neglect the right-hand side, which is the time-dependent term. And we can also say there's no heat generation. Then you can neglect this one. And you can also say this is one-dimensional heat transfer in x direction. Then you can neglect these two. So the remaining is going to be dx dt square over dx square is going to be 0. This is the simplest heat conduction problem in steady state one-dimensional heat transfer. Okay, so we are going to study this one first in chapter 3, one-dimensional steady conduction. So what is the governing equation? The governing equation is going to be this one. If we assume steady state, one-dimensional, steady state, heat transfer, and thermal conductivity K is constant, then the governing equation is going to be dt square over dx square is going to be 0. Or you can say we still have heat generation. So this one is without Q dot, and with Q dot, one-dimensional, steady state, when thermal conductivity is constant, then the governing equation is going to be dt square over dx square is going to be minus Q dot over K. So these two are the main governing equations that we are going to study in this chapter. So we are going to study the first without heat generation, that is the first part, and with heat generation, which is the second. And we are going to study a unique one-dimensional heat transfer, which is called fin. So that will be the third part of this chapter 3. So we are going to study these 3 items in this chapter, okay? So in your first exam and in your second exam, which is the first exam of heat transfer, you will see 3 or 4 problems among these 3. And in chapter 5, we are going to study transient heat transfer, transient conduction problem. So what is transient conduction problem? Heat transfer depends on time. So what is the time dependent term on the heat equation on top? The one on the right hand side. So when we go to chapter 5, we are going to study one-dimensional, K is constant, without heat generation, but transient. That is going to be the first term on the left-hand side and the right-hand side. So the equation is going to be the second order partial differential equation with respect to x is going to be 1 over alpha partial t temperature over partial time t. So this is the equation that we are going to study. And there are 2 different ways to study this equation. One is called a simple lumped system and approximate solution. So there are number 4 and number 5. So there are 5 items that we are going to study in terms of heat conduction, and you will see 3 or 4 problems among these 5. So that's how you can prepare the second exam, okay? So what we are going to do today, we are going to study number 1, and next week we are going to study number 2 and number 3. The following week, number 4 and number 5. Then what comes? Exam. Very straightforward, right? So that's what we are going to do, okay? Any question about our plan? No? Okay. Similar to the first exam, I disclose everything, right? So you knew what was coming in the first exam, right? Now you know what is coming in your second exam. So I guess that, that this help you, prepare for the next coming exam. So let's talk about one-dimensional steady state constant thermal conductivity without heat generation. So here is the governing equation. The simplest case, one-dimensional steady state, no heat generation. Then the governing equation is going to be this one. Oh, wait. We were talking about dt square over dx square is going to be 0. Then what is this one? This is the backup form of this differential form. As I told you, this upside down triangle means each upside down triangle means partial over partial x in the x direction plus partial over partial y j direction plus partial over partial z and z direction. Each of them. So this is where your variable next to this triangle, upside down triangle, goes in. Now, how many of them? We have 2. So this one multiplied by another upside down triangle. What is it? Partial over partial x I plus partial over partial y j plus partial over partial c k. So now we are going to multiply these 2. And if we have 2 upside down triangles, we are going to multiply by the dot product. You know how to do dot product. Multiply these 2 when it is I times I, that means 1, I times j, 0, I times k, 0, j times j, 1, j times I, nothing, j times k, nothing. So you only consider I times I, j times j, and k times k. Since we have t, we can add t here, and this one multiplied by this one. What is it? Partial t square over partial x square. What is I times I? 1. So there's nothing after. Plus partial t over partial y times partial over partial y. What is that? Partial t square over partial y square times j square. What is j square? 1. The last one. Partial t square over partial z square is going to be what? Excuse me. Is going to be 0. So this equation, which is called the Laplace, looks like this one. And we are only considering one-dimensional heat transfer. So among x, y, z, which one do you prefer? X. So we can say this one goes away, this one goes away, and what this one looks like here. Why this is a partial, why this is d? This is ordinary differential equation. This is partial differential equation. We use a partial differential equation when we have x, y, z more than 1. Now we only have 1, so you can replace this partial with d. A brief mathematics, but that's over. No more mathematics. Okay. So basically, what we are going to study is this equation. Then, how can you solve that equation? What do you mean solving this equation? It means that we are going to integrate twice, right, with respect to x. So how can you integrate? First, dt over dx is going to be some constant, c1. Let's integrate one more with respect to x. T is going to be t1 x plus t2. So that is the general solution. Very easy, isn't it? Temperature T is C1, a constant C1 times x plus another constant C2. Then, that is the mathematics. So let's talk about this equation physically. Here, we have a plain wall, and let's see, how this equation look like. T plus C1 x plus C2 on a plain wall. So we have plain wall like this. Let's assume that this is the wall behind this whiteboard, and let's say that this is the other side is outside. So outside is a little chilly, 0 degrees Celsius, and inside is 20 degrees Celsius. Then what do we expect? We know there is a heat transfer. We know there is a heat transfer because there is a temperature difference. So what is the direction of heat transfer? From 10 to 20, right? Of course not. From 20 to 10. So the heat transfer direction is from high temperature to low temperature. Q, the rate of heat transfer. Why from high temperature to low temperature? Because of the second law of thermodynamics, heat transfers from high temperature to low temperature. Then, what kind of heat transfer, that occurs in this problem? First, this is solid. What about here? Air in the classroom, air outside. So between fluid which can move and a surface, so we have convection. So from here to this one, this is Q by convection. And through this wall, can this, the solid molecule can move? No, so it's going to be pure heat transfer, conduction, Q by conduction. And outside, on the outer surface of the wall and the surrounding air, which is wind, Q by convection. Then, since we are studying conduction heat transfer, let's talk about here. Then, how this temperature distribution look like. First of all, here is 20 degrees Celsius. To have a heat transfer in this direction, what's going to be the temperature on the inner surface? 20? If the temperature is 20, is it possible? It's not possible. If it is 20, this one is 20, there is no temperature difference, so there is no heat transfer. And since there is a heat transfer, the temperature at this inner surface should be less than 20 degrees Celsius, right? So let's assume that the temperature at this point is 18 degrees Celsius. What about the temperature on this outer surface? Should be less than 18. What about the temperature is greater than 18, like 19? Then there is no heat transfer in this way. The heat transfer direction should be this way, which is against our assumption. So the temperature on the outer surface should be less than 18. What about the temperature between this outer surface and air in the outside? The temperature here should be less than 18 to have a heat transfer in this direction, and this should be greater than 10 to have a heat transfer in this direction. So let's say temperature is around 14 degrees Celsius. Then what is the temperature distribution from 18 to 14? This way or this way or this way or this way. So such as 18, 17, 16, 15, 14, 13, 12, 13, 14. Is it the temperature distribution? No. Then this red, this green, how do we know? We know because our governing equation is this one. T is C1x plus C2. According to the heat equation, T should be C1x plus C2 when it is Q by conduction. So T is C1x plus C2. What is T? This vertical axis. What is X? This horizontal axis. So this is T, this is X. Then what is the relation between this point and this point? Should be straight line, like this. This is the temperature distribution inside, 14 degrees Celsius. So from that heat equation, from this differential equation, Td square over Tx square should be 0. We now know the temperature distribution within this, the solid should be first order, flat, okay, straight. Make sense? So heat transfer temperature distribution shouldn't be this one, shouldn't be this one, shouldn't be this one, or this one. dot, this blue is the temperature distribution. Then what about this convection? Convection heat transfer is heat transfer between a moving fluid and a surface. So between the surface and far away compared to between the surface and nearby, which one is more significant? So let's say that this one is like a stove on the wall. Doesn't make sense, but let's assume that this whiteboard is very hot. Then if I standing right next to it, I feel like it's very hot, right? Heat transfer is very significant. But if I stand on the other side of the the classroom, do I feel that heat? Not much. So when it comes to convection between a surface and the surrounding fluid, only near the surface is significant compared to far away. So the temperature distribution should be very significant near the surface, which is very significant, and become negligible far away. So that's the temperature distribution. What about here? Very significant. Dramatic change in temperature and become meaningless. So the temperature distribution from 20 degrees Celsius down to 10 degrees Celsius outside is going to look like this. Okay? So you need to understand, how temperatures are distributed in a heat transfer problem. First, understand the physics, then you can solve mathematical function. Okay? So don't just write down, okay, so this is the heat equation, this is the Fourier's law, this is the Newton's law of cooling. Don't write down the equation before you understand how the temperature look like. Okay? Now, if I just want to study this heat transfer within a solid, is it difficult? The conduction heat transfer? Not much. The equation is pretty simple. T is T1x plus C1x plus C2. Then, is it hard to determine C1 and C2? Not really. Not really. Let's assume that this is when x is 0, and let's assume that this is when x is 1. When x is 0, temperature is 18. When x is 1, temperature is 14. Then this C2 is going to be 18, and C1 is going to be minus 4x plus T. So this is the temperature distribution in this case. So understanding heat conduction only is very easy, as long as it is steady state. Now, what makes this heat transfer problem complicated? We have a convection here. We have a convection here. So this heat transfer is not just pure conduction. It is a combination of convection, conduction, convection. That's what that makes this heat transfer complicated. Then we want to know how can we study heat transfer when we have conduction, convection together. The simplest way to understand conduction, convection together is called equivalent thermal circuit. So we can use equivalent thermal circuit to understand heat transfer problems when we have conduction, convection together. Okay? So we are going to use we are going to use the same the analogy between electric circuit and heat transfer. So when you have electricity passing these 2 points, so this one is V1, this one is V2. The electricity is passing this resistance, whose resistance is R. Then what is the electricity? What is the current? Current is I. I is going this way. Then what is the relation between voltage, current, and resistance? Yes. Or you can say I is the difference in voltage divided by resistance, right? So V is IR. Similarly, in heat transfer, we can also use the same resistance concept. That is called thermal resistance network. So in this case, instead of V1 or V2, we are going to use, this is very important, temperature, T1 and T2. And between these two temperatures, what do we have? Between these two temperatures, we can have conduction, convection, radiation, or anything. Then each conduction, convection can be a single resistance. Thermal resistance, which is R of T. Thermal resistance, or you can just say R. And instead of current, what do we have? The rate of heat transfer, Q. Then heat transfer rate Q is going to be the difference in temperature over thermal resistance R of T. So that's how you can use this thermal resistance network. Then, is it hard? Not really. You just need to know how can we determine this R for, let's say, conduction or convection. So let's talk about the same example previously. We had a wall. We have this wall. This is solid wall. And there's a temperature inside 20 degrees Celsius. And the temperature outside 10 degrees Celsius. We know the heat transfer direction is from 20 to 10. This way, this is the heat transfer direction, Q. And this is not just Q. First, we have convection heat transfer, let's say Q by convection. And conduction heat transfer, Q by conduction. And another convection heat transfer at the end. Since we have two convection heat transfers, I'm going to say this is number 1, this is number 2. Then each heat transfer can be counted as one resistance. So we can say this convection resistance is here between 20 and the inner surface, whose temperature is unknown. So I'm going to say T1. And so this is convection resistance, R of convection, number 1. And we have another resistance to represent conduction heat transfer through this wall. I'm going to say the outer surface temperature is T2, and the resistance is going to be R of conduction. And we have one more resistance for this convection outside. R of convection. Number 2. So at the end, we have temperature T 10 degrees Celsius. At the beginning, we have 20 degrees Celsius. This blue that I wrote is thermal resistance network. So now you only need to know how to determine R of convection, R of conduction. R of convection is one over H convection coefficient times cross-sectional area, which is the surface area. And this conduction heat transfer is delta X, which is the distance. So this is delta X. Divided by thermal conductivity K of this wall times cross-sectional area. And finally, we have a conduction resistance at the end that is 1 over HA. We have two H's, so I'm going to say the left one is going to be HI indoor. The other one is HO outdoor. Then we can come up with this equation, Q, the rate of heat transfer or heat rate, there are many names, is going to be delta T over the sum of resistances. Then what kind of delta T? We can use 20 degrees Celsius and 10 degrees Celsius. So in that case, Q is 20 degrees Celsius minus 10 degrees Celsius divided by how many resistances between these 2 points? 1, 2, and 3. So I'm going to write all the resistances here. 1 over HI times area plus the thickness delta X over KA plus 1 over the convection heat transfer coefficient H of outside times area. So that's how you can determine the rate of heat transfer, Q. Is that it? No, you can come up with many different Q. You just need to follow this, the form, delta T over the sum of R. What about if we consider 20 degrees Celsius and T2? You can do that. So the same Q is going to be this time between 20 and T2. 20 degrees Celsius minus T2. How many resistances between 20 and T2? 2. This one and this one. So you can say 1 over HI times area plus delta X over KA. Is that it? No, you can come up with another temperature differences. But this time, delta T is going to be T2 and 10 degrees Celsius. So you can say this Q is again, now this time between T2 and 10. T2 minus 10 degrees Celsius, and how many resistances between these 2 points? Just one, convection resistance. 1 over HOA. So that's how you can come up with this heat equation. So what you can do is, since you do not know the rate of heat transfer, you can solve this equation to determine this Q. And you can solve this equation to determine T2. And you can solve another equation in order to determine T1 or any unknown. So depending on the number of temperature points and the resistances, you can make many different Q is delta T over R. Okay? This is called thermal resistance network. Any question? This may not be enough. So let me give you, another example. Now, this time, I'm going to make multiple layers. Rather than one, I'm going to make multiple layers. So, this time, I'm going to design a building whose wall has, let's say, 10 centimeters. The thickness is going to be 10 centimeters, 0.1 meter, whose thermal conductivity K is going to be some number. So let's say K is maybe 2 watt per meter Kelvin. And what about the surface area? The surface area of the wall. I don't know, maybe you can consider the unit area. Area is going to be 1 square meter. But if you design a building with just this single wall, you may experience a lot of heat transfer. So in winter, it's going to be very cold inside. In summer, it's going to be very hot inside. So what do you want to do? I want to add some insulation. So I'm going to add some insulation. The insulation has a thickness, let's say 0.07 meter, whose thermal conductivity should be very low, right? It's an insulation material. 0.1 watt per meter Kelvin. But when I add an insulation, it looks ugly. So I'm going to add what? A drywall, right? So let's add a drywall. So this drywall has a thickness. How thick? Maybe 1 centimeter, 0.01 meter, whose thermal conductivity may not be as good as this insulation. So K is going to be a little high. So K is going to be maybe 5 watt per meter Kelvin. And after this insulation, after this drywall, that drywall looks ugly. So I'm going to paint it. So I'm going to paint it. What color? Red. Where's my red? Okay, red is too much. Blue. So there's a blue paint on top of it. And why so funny? Okay. So this blue paint, whose thickness, delta X, is going to be very thin, 0.005 meter, whose thermal conductivity, K, is going to be maybe 10 watt per meter Kelvin. When I look at the outside is also look ugly. And these days, the people install a glass on the wall, right? Now, if you go to Chicago or Detroit, all the fancy building, what about the one, Sears Tower? It's made of glass, right? It's not Sears Tower anymore. What is that? Willis Tower. So I'm going to add a glass. Looks reddish glass. Because I only have blue and red, so there is no more color. I have green. So this green glass on top of it. So whose thickness is going to be 0.00, and that's too thin, 1 meter. And thermal conductivity is about 1 watt per meter Kelvin. Now, what do you want to do? I want to What do we want to do? Okay, I want to transform this building to be a giant freezer. So I can put some, the frozen fish inside. So inside is going to be very cold. The temperature inside is going to be minus 20 degrees Celsius, freezing inside. Outside, warm, 20 degrees Celsius. Then what do you expect? There's a heat transfer from minus 20 to 20, right? Like the Iceman, they're trying to throw some ice. That's not possible in heat transfer. It should be the other way, right? Anyway, the observing heat rather than, the shooting ice, right? No? Haven't you seen that, the X-Men or something? The guy is, the making ice by giving something that is completely wrong because you need to observe to make ice, not releasing, right? Anyway, so the direction of heat transfer should be this way. So there's a Q. So what do you want to do? To maintain a constant temperature inside, to maintain minus 20 degrees Celsius inside, you need to run a lot of refrigerators, right? Like a refrigeration system. Then you need to understand, you need to determine how big this refrigeration system should be. That depends on the rate of heat transfer. So you need to, you need to run a refrigeration cycle to remove heat in the same amount of this Q so that you can maintain constant temperature inside. So let's determine this Q. How can we do that? You can use thermal resistance network. By the way, inside the refrigerator, inside this, the freezer, there's not much, the air movement is going. So convection heat transfer coefficient, HI, is going to be very small, like 1 watt per meter Kelvin. But outside, it's one of the windy day, so H outside is going to be pretty high, 20 watt per meter Kelvin. Okay, so let's determine this Q. We can use thermal resistance network. How many resistances? First, we have a convection here. So there's a minus 20 degrees Celsius, and we have convection heat transfer. And what else? Blue paint. What else? Drywall. What else? Insulation. And the wall. And glass, the green glass. And finally, convection outside between the outer surface and 20 degrees Celsius. Then what is the convection heat transfer resistance? The convection resistance, 1 over HI times area. And what about this conduction resistance through this blue paint? Delta X over KA. So this is blue glass. I'm going to say number one. And we have a drywall, delta X number 2, K number 2A, and we have what? Insulation, delta X number 3 over K number 3, and area, and the wall, delta X number 4 divided by K number 4, area, and the green glass, delta X number 5 over K number 5, area, and finally we have a convection resistance outside, 1 over HO times A. Heat transfer direction is this way, Q. And how can you determine this Q? Q is going to be delta T over the sum of resistances. So what is delta T this time? 20 and minus 20. 20 degrees Celsius minus 20 degrees Celsius. And how many resistances? 1, 2, 3, 4, 5, 6, 7. First is this one. 1 over, what is H? 1 watt per meter square Kelvin. 1 over 1 watt per meter square Kelvin. What about area? I'm going to say the unit area. 1 plus the thickness of the paint, 0.005. What is the thermal conductivity of the paint? 10 times unit area. Plus the thickness of this drywall, 0.01, divided by the thermal conductivity of drywall, 5 times unit area. Plus the insulation. The thickness of the insulation is going to be 0.07, and the thermal conductivity is pretty low, 0.1 times unit area. And the thickness of this wall is going to be 0.1 divided by thermal conductivity 2 times unit area. And finally, we have this glass whose thickness is 0.01 divided by thermal conductivity 1 times unit area 1, plus the convection resistance, this one, 1 over H. H is 20 because it's windy outside, and the unit area. That's how you determine the rate of heat transfer Q. Now, once you determine this Q, let's say I want to determine the maximum temperature of the insulation. Let's say, let's determine the maximum temperature of insulation. Where is the maximum temperature of insulation? First of all, this is the insulation. And how many temperature points in this insulation? The inner surface of the insulation, the outer surface of the insulation. Which temperature is greater than the other? The one on the right, the one on the left? Or are they the same? Let's say this one is T1, this one is T2. This is the insulation. The green is the insulation. How many of you think that T1 is greater than T2? T2 is greater than T1? Or are they the same? You're right. T2 is greater than T1 because the heat transfer is in this direction. If T1 is the same as T2, there's no heat transfer. If T1 is greater than T2, heat transfer direction is the other way. So to have heat transfer in this way, T2 should be greater than T1. So if you want to determine the maximum temperature of the insulation, you need to determine T2. So let's determine T2. How can we do that? So let's assume that we know what is Q. I'm going to make another Q equation, but this time between T2 and 20 degrees Celsius. So what is delta T? 20 degrees Celsius minus T2. How many resistances between these 2 points? One through this wall, one through this glass, and one by convection. So there are 3. So wall first, the thickness 0.1 divided by 2 times unit area plus 0.01 divided by thermal conductivity 1 times unit area plus 1 over H, 20 times 1. So, assuming that you already calculated the heat rate from the previous equation, you can determine the maximum temperature of the insulation. That's the temperature only in the phase between insulation and the wall, because insulation has many temperatures in the direction of heat transfer. There's no just one single temperature. If there's only one single temperature, that means that there's no heat transfer through that insulation. There's to be temperature gradient in the insulation to have heat transfer through that insulation. Okay? So when I ask, what is the temperature of insulation, that question is wrong because it should depend on the location in the insulation, right? Yes. That R value is this one. Mm-hmm. You need to check the unit. Unit could be different. But this is how you determine R value. The concept is the same. That's what we are going to do in the next slide. So here is the simple explanation when you have a multiple layers and when there is a heat transfer. So we basically use the same equation to determine Q, which is delta T over R. And in many cases, not in mechanical engineering, but usually in construction engineering, when we design a building, when we design a house, and like those big ones, some people like to use overall heat transfer coefficient, which is actually the same as thermal resistance network. Instead of 1 over R, they prefer to use U, which is the inverse of R. So don't get confused when you hear overall heat transfer coefficient, which is the inverse of thermal resistance. Okay? So this is the question, this is the answer to your question. What about if we have a parallel composite walls? So we have two different materials are in parallel in the direction of heat transfer. Then, if we have, the multiple layers, then you can just add to calculate the sum. But what about if we have a parallel walls together? Then, the way to combine these two is the same as how you combine, the two resistances in parallel. So let's say that this one is R1, this one is R2. You can combine them by using this one. 1 over combined resistance R is going to be 1 over R1 plus 1 over R2. Then you can use this R and say there are only 3 resistance. So you can use this R to represent R1 and R2 are in parallel. Okay? I can promise you that there will be at least one problem that you need to use this thermal resistance network in your second exam. Any question up to here? This thermal resistance network is what we are going to use in the field to analyze thermal management system. Simple, but very powerful. So you can use, in many steady state heat transfer problems. And your question is going to be, how many times, are we going to see a steady state heat conduction problems? Most of engineering systems are steady state. So when you work for a cell phone company, heat transfer from the cell phone is going to be steady state. When you work for the computer company or this screen, heat transfer from the screen is going to be steady state. Why? If it is not steady state, it should be transient. That means that initially 20 degrees Celsius. When you turn on, it's going to be transient. Let's see what's going to happen if it is transient heat transfer problem. Initially 20, 10 minutes later, 30, 20 minutes later, 40, 30 minutes later, 50, and an hour later, there's a fire in the house, right? So most engineering systems are steady state, and the way you study their heat transfer are going to be most likely thermal resistance network. That's important. When you work for the car company, they're trying to understand how engine works. Where do you study heat transfer? How you maintain constant temperature of what? Cooling system. So is that cooling system steady state? It should be. If it is transient, that's the day you need to buy a new car, right? What about this cell phone? Many people talk about the battery system. Many people talk about EV. What is the main cost of EV? The wheel, the window, the batteries. And what is the critical factor these days when we talk about battery systems? Their thermal management. If you fail, there's a fire. Okay? And how can you, study how much heat transfer, that you can expect when you are using this battery at this rate? Thermal resistance network. Looks very simple. However, that it will be used in many, many places. Okay? But before we finish thermal resistance network and start solving problem, there's one more thing that we need to talk. In the previous example, we studied there are multiple layers like this one. So there's a wall, there's an insulation, there's a drywall, and there is a paint, glass, etc. But this does not reflect the reality. The reason is that when you add insulation on this wall, the contact between insulation and the wall may not be perfect. How many times you can expect a perfect reality? This is what happens. Usually imperfect contact between two solids. Then what's going to happen in terms of heat transfer? If it is perfect contact between two solids, then let's assume that this side is 20 degrees Celsius, the other side is minus 20 degrees Celsius. We expect there are two resistances. First, through this wall, by conduction, number one, and another resistance through this wall by conduction, number two. So there's a minus 20 degrees Celsius, there's a 20 degrees Celsius. However, in reality, the contact may not be perfect. So you may have this much gap. Then what's going to happen? This is 20. This is minus 20. So we have a conduction resistance. Then what's going to happen? Between this surface and the gap, what do we have? Convection resistance. So there is convection resistance. Then from the gap to this surface, there's another convection resistance. Then conduction resistance. By having this imperfect contact, how many resistances now? There are 4 of them. So does it affect the heat transfer? Yes. Depending on the size of this contact, depending on the size of the gap, it can dramatically decrease the heat transfer or not. Okay. So we need to know how to deal with this contact resistance. And typically we use a table to account for the resistance due to imperfect contact between 2 solids. So the first one is a vacuum interface, meaning is that there is no, the fluid in the gap, or there is a fluid in the gap. So depending on, how much pressure has been used to, to put these 2 solids together, these are the resistance numbers, R numbers for different materials. Then, how can we use this contact resistance in your exam? If you need to use this contact resistance, I'm going to write in the problem statement, this is the contact resistance. So please take this one into account. If I don't say such a thing, you can assume that you can neglect contact resistance and then solve the problem. Okay? Of course, if you need to consider contact resistance, then I'm going to provide this table so you can use it and then pick the number, make sure that the unit is correct, and then write, the add into your Q is delta T over R equation. Okay? Any question? So that's everything about thermal resistance network in Cartesian coordinate system. Then when you know what's going to happen next week. Thermal resistance network in a different coordinate system. And there are many coordinate systems, but we are going to focus only 2 coordinate systems, which are most widely used in engineering systems. Of course, Cartesian coordinate system, and the other one is much more useful, especially you are mechanical engineers or electrical engineers, cylindrical coordinate system. So heat transfer from a pipe, heat transfer from an electric wire, those are the critical things. So we are going to study how to determine the rate of heat transfer from an electric cable or the water pipe or air duct. That's what we are going to study on Tuesday next week. And then there are a couple of problems. So we are going to solve them together. Then that will be all for, where's number 1 to 5? Then that will be all for, I don't see it, thermal resistance network, which is number 1. I show you, the number 1 to number 5, the earlier today. So that will be number 1. And then the following day, we are going to talk about steady state heat conduction problems with heat generation. That's the number 2. Then fin, number 3. Then transient heat conductions, there are 2 methods, 4 and 5. So if you complete all 5, then you can have 1 exam that has 3 or 4 problems among these 5. Any question? That's it. See you next week. Oops, we still have 4 minutes.